Okay, let's start. So, what all my presentation is about. Making computing parallel. For very many years, humanity, I can estimate in 100 years, it started in early 1900s when mathematicians started formulating the language of mathematics with set theory, trying to describe how logic works, how you can shift between propositions, how you can prove things. And they started seeing patterns in mathematics, in the language which describes mathematics. And at some interesting point in mathematical theory development, they discovered this concept called lambda calculus, which became foundation for many compilers and functional programming languages. And apparently, another mathematicians, not those who invented lambda calculus, were playing with even simpler, more basic concepts, trying to reason about what computation is. How many of you were asking question, so how this bit shift works? What happens? Okay, let's remove all the bits and think about just computation of addition. We can imagine how these things work when we just write down using paper and calculation in mind. But what computation as a process is, what's going on when thing computes from one state to another, and what is the result, what is the effect of this? So mathematicians were asking this question for 100 years, and that's where all our foundations for computer science, for programming came from. How many of you heard about Turing machine? How many of you at least approximately understand how Turing machine works? The basic operating principle of Turing machine. So it's a tape of instructions, very long tape. In Turing definition, it should be infinite if you want to be Turing complete. And you can write instruction, move farther left, move right, save something in your register, and depending on the state of that register, decide where to move next. Turing machine is inherently sequential. So we're talking about parallel computation here, and Alan Turing, who helped us to win the war, unfortunately designed this model of computation being linear and sequential. So it doesn't scale very well. You can create many parallel machines running, doing something in parallel, but you will face the point in time where you need to actually converge the results of your data and merge them and maybe distribute again. So, Alonzo Church, who invented lambda calculus, was actually contemporary of Alan Turing, and they were working together, and they proved Church-Turing thesis showing that Turing machine and lambda calculus are equivalent, and they are completely computationally complete and allow to write any program. There are other classes to make computation complete, and since that time they were explored. And modern processors basically are kind of small Turing machines with von Neumann architecture. Who heard about the concept of von Neumann architecture, at least the formal name of it? And the answer is, all of you know what that is. That is CPU, that is memory, that is bus sending messages between, and that's instruction set, which get parsed, fetched from the memory, and instruction by instruction executes basically memory moves all over the place. That's how all modern processors do work. And you can see here we have the same sequential process going. So it's not very parallel. Many people believe that we solved the problem of parallel computation because we have these giant data centers, we have big supercomputing machines where we have very many small cores. They have very complex networks connecting every processor with one another using kind of their internal internet. but it does require that engineers actually create architecture for these processors and write special software which actually packages all these data packets and packs. So each processor still, when the computation goes through one CPU, you are in that mindset of one instruction at a time, one step after another. So let's talk about what are the alternatives of this von Neumann architecture. And if you see any functional programmer, they will be blaming you for imperative programming style, like our functional programming is much cooler than your imperative. You guys, Java programmers, C programmers, don't know what you're doing because our code is inherently parallel. We work on lambda trees. And that's partially true, but unfortunately they faced their own problems trying to make functional programming practical and fast. We don't have a functional programming language compiling to operating system because it's not very fast. And the reasons I would love to explain in detail, but it will take some introduction. So I want just to cover what attempts have been made to achieve this parallel computation. So we strike out Turing machine and von Neumann architecture because we can add supercomputers, okay? This is the best attempt humanity made to achieve using Turing machine, achieve parallel computation. The limitation of this approach is it doesn't scale on its own, and every process, every computation is inherently sequential in every single core. You can have maybe a million cores, I'm not sure how big they are, didn't explore that, my bad, but they are still sequential. Some approaches have been used, and the most modern approach was from 1995. Who of you heard the abbreviation FPGA? Those are field programmable gate arrays. Very many Bitcoin blockchain miners trying to use them, so they can just put this Bitcoin algorithm in it, and they run and they make them very warm, and they crank the numbers which are specified to do specific work. Also, these devices can be imagined as you want to create electronic device, digital electronic device, and it's too expensive to order manufacturing of silicon chip. It's $40,000 plus, depending on the resolution, and you can just order a device which allows to reprogram itself, and it allows you to reconfigure its logic gates, reconfigure the way how what it exactly does. So you can create conventional von Neumann architecture processor out of this device. The difference will be the clock rate. It will be lower, not that fast. That's what they use FPGAs for. But FPGAs don't solve the parallel computation problem. Only if you not program them to run some hard-coded, hardwired, pre-programmed, but hardwired. After you programmed it, it runs the same algorithm without reconfiguration. Data signals don't change the way how it computes. So, and we were using them since probably late 70s, and they're famous everywhere. Microsoft uses FPGAs for their Bing servers to accelerate processing, because these things do computation which is specialized, which is not general computation. Processors in our phones and laptops do general computation. They can crank any numbers for any general purpose. And they are universal Turing machines which just merge data and work on shared memory. So in 1990, I would say he started research from 85, influenced people who were designing FPGAs. And a guy from Germany, Reinhard, you can Google his name and the research looking for X-Puter thing. So Xputer was trying to create reconfigurable FPGAs and influenced entire industry with languages describing how they design just ordinary processors nowadays, using tools to create wirings and then manufacture microchips. But his dream was to create universal computational device which can reconfigure itself while running. They achieved some very good, significant results. They either had problems with promotion of their ideas, or they just faced limitations of their orthogonal design. But I would like to talk about the details of this later in more specific context. Just telling that this example was the best example where we truly achieved something scalable, something truly parallel and reconfigurable, and this example is the closest one to my research. So if you want to look it up, it is Xputer thing. Many other attempts have been made to make computation parallel. I think that was fall. As I already said, lambda calculus is another model of computation which was competing with Turing model, and Alonso Charge, who invented it, was always proving Turing that no, this is better because it computes everything in every point. So lambda calculus has an interesting property called beta reduction. It's not exactly property, it's a process. Beta reduction is a process, but property, I forget the exact name. It allows you to do computation in all parts of a binary tree of functional applications simultaneously everywhere, and it doesn't matter what is the order, the result of reduction is always the same. And there was SKI combinator calculus. This is a core engine running under lambda calculus. They found direct mapping, and surprisingly enough, combinators were invented before lambda calculus formal description was provided to scientific community and proven to be Turing complete. And that's fascinating. And it happened that these SKI combinators are the core building blocks of computation. You can only use two combinators S, and they have concept of function application, and K. You can Google Wikipedia about how they work, and because these things can answer your question about what computation is. Without showing the details, because we're probably running out of time, they create duplicates and shuffle mutual applications of different parts of a binary tree, or they get rid of another arguments, so get rid of parts of the trees. All this beautiful thing works and proven to be Turing complete, and actually functional programming languages do compile into this mode efficiently. And an attempt was made to create hardware implementation which runs this beta reduction process. As I said, there is direct mapping between lambda calculus and SKI combinators, so it's possible to do mutual transformation of your functional code into combinators and vice versa. And guys created a processor called reducer-on. As you can see from the name, it does reductions. It runs combinators. It operates not only S and K, there are very many different classes. There is an interesting site called Combinator Birds. And it's all great for functional programmers, but what problems these guys faced? In order to reconfigure all these binary trees, one can discover very quickly that they do very massive moves of complex structures. And when we implement these trees in the physical world, we need to keep pointers, we need to do switches of how do we search, what is our connectivity scheme today. And Apparently, they faced these performance problems and scalability problems when they were trying to move massive arrays of memory. So, unfortunately, they faced the same limitation we had with von Neumann architecture, where we have to move, and that's where the all excess heat is dissipated. By the way, good news, this guy who invented Xputer proved that this reconfigurable computing can 10 times and even more decrease the energy consumption of modern computing systems. So imagine how big impact it can have on data centers. But I have bigger goals. Well, what we need scalable computing for? Just imagine what scalable computing can mean for us, not just software engineers, but for the entire world. What capabilities can become open for us if we actually achieve that dream? We can just add more processing power, more modules to it, and it can compute more complex program. We can build supercomputers just adding more chips to it. We don't have to engineer supercomputer data centers. We just build another supercomputer center, right? Connect cables, and here you go, and it all computes. And we can keep scaling up as long as we have enough resources to manufacture the chips, right? And the connectors. And people who want to predict weather, for example, or launch ships on very distant planets or mine asteroids, can run their simulation and computation on this thing, understanding that, yeah, they have access to this power. And unfortunately, engineers have to solve problems of every next level of scalability by hand, thinking very, very heavily about what they can do in order to add more interfaces. And it actually very simple. Who studied anything about management or was trying to lead a group of 3 or 4 people? If you have 3 people in your team, you have only 3 interactions. If you have 4 people on your team, you have 1, 2, 3, 4, 5, 6 interactions. If you have 5 people on your team, the number of interactions grows very quickly, and so on. If you add just one more node, the interconnectivity, possible connections between them increases exponentially much faster than you add the new nodes. So this limits scalability just using ordinary interfaces, because you have to build more broadband interface every time you build bigger data center or bigger supercomputing device. As I said, attempts have been made, but they don't scale. I promised about molecular computing. They actually implemented an entire idea of SKI combinator calculus running on analog of molecular machines, but they faced the same problems with moves of big trees and tracking resource allocation and the geometry, tracking of the shape rotations, making sure that everything will be connected in predictable way and never get broken. There's interesting papers on that theme, and I would love to share with you later. I believe very many follow-up links should be provided here. So all these attempts to scale have failed. As long I think Xputer was the best interesting thing. So who of you saw Game of Life videos? Okay, so who knows what Game of Life approximately is? Can you explain? Can you explain?
I've only seen like maybe one video of it. It's like a simulation. That's all I know.
It is simulation. Simulation is a good word because they're trying to run some abstract model using homogeneous lattice of sets. And the rules there are very simple. They depend on the number of neighbor cells If you have three neighbor cells, you're probably going to die. You have overpopulation. If you have only one cell alive, you also going to die. It's too lonely. And things like that. And they discovered that rules simple like this, there are only four rules describing exact neighborhood, allow one to write Turing complete computation thing. And they created giant Turing machine in this and proved that it actually works. But it's so giant, it's absolutely impractical, and for many years, cellular automatons weren't a practical model of computation. But they have a great property. They have homogeneous lattice. So if you add more elements here and there, you can scale your data center, right? Should you stop ever? It's great, right? It's infinitely scalable. We would love to use this approach, but what's the problem with it? Propagation delay. We can have elements right here, and every update allows to deliver maximum one cell. So we need to use these clock cycles. We need to run this simulation over and over for this thing. So the signal comes here again at some time. But we have this great thing called speed of light, and it's very quick. Much faster than like distance between your elements you can manufacture. But still slow. We have 5 millimeter distance nowadays. Modern processors, modern switches in all semiconductor devices can turn on, turn off packets of radio waves, photons, electrons. They kind of converge there, wave particle duality thing. So they have changed packets between different 5 millimeters. So if you have chip, say 15 millimeters wide, one parts will be on and another parts will be off just because light didn't reach it yet there. So, but still, the speed of light is fast enough, and we want to use delivery of signals much faster than just grid lattice propagation delay. It's still too slow. It's not satisfying model. So my invention idea was, let's support non-local dependencies. Have some cell here and some wire work going directly to this cell. I can arrange all these intermediate cells in this synchronized manner. Like I told this cell, okay, turn your shape in such a way that it will get signal from the left. And you can keep arranging them, and it will take time. Of course, you need to program this system, but in the end, you created this programmatic wire, and you create cellular automaton with non-local dependencies. I tried to write this in software and play it with code a little bit to see how, what's the view of the patterns it develops into, and I was highly surprised that they actually generate patterns looking very differently from the classical cellular automaton. I posted it on generative programming, got some 33, 35 likes. People said, wow, awesome, show the code. I'm not showing my code yet, but I will publish it later on GitHub, and interested people can actually participate in moving that paradigm a little bit further. There's a lot of work still left, and I would like to showcase these things, but it will take just 5 minutes, so we can talk 5 minutes more about this, and it will be quite simple to run probably. So what is our roadmap? I actually wanted to talk with you about functional reactive programming and pure functions. My bad, 30 minutes is not enough to get this introduction of why this background, where this all came from. So we should plan on the way how to think about ordinary code and how to transition from ordinary Java or C++ or even C code and write down simple version in cellular automaton. And I have that answer. An answer came with another intermediate block called membrane computing. Who watched The Matrix, the movie? The Matrix. So remember they had these programs, and they kind of had their own process going on inside. They see us, they think on their own, they make decisions, then they say something, or they walk somewhere, or trying to escape parts of the Matrix too, right? And I was thinking since late 90s, how they can use this perception, internal processing, and then actuation. How everything can be encapsulated in just inputs and outputs and some internal structure. And that's where object-oriented object-oriented design coming to save us, helping us to do encapsulation of smaller, lower abstraction levels. And we can build extremely complex systems because of this virtue of encapsulation. Encapsulation is actually the best thing invented either by people or by nature, but we have this gorgeous thing where we can just assemble complex hierarchy of connections and then just wrap them into a package and forget about how they exactly connected inside. So my machines, using these non-local dependencies, allow to express these complex interconnections inside and redefine them based on inputs which come in as your arguments. Imagine that you're just calling a method and passing some value. And this thing can work that way that your value get interpreted as the description how some of internal components should be connected with one another. And because we have this ability to build these wires which go very far from one place to another, we have this ability to reconfigure where wires go. I would like to talk about these multiplexers later, bless you. So because they are a hardware implementation of this thing, but they have not very much in common with real computer science, like abstracting. It's just detail of implementation. They're controllable switches. If you have two inputs, right, and you want to say, you want to select this one, you say 1. You want to select this one, you say 0. And that is it. And you have only one output. And you can add either 0, either 1 on its input. And inside they have this controllable switch. And it can be either there, either there. It's a very simple construct, basically. And I discovered that my elements are basically ultimate multiplexers. That's what they do. They have control and input. And you can define their next step. Just let me show you how this cellular automaton look like when you just launch it as a simulation using random code, just like cellular automaton or game of life enthusiasts were trying to do. Oh yeah. So I just used these new nodes, multiplexers. In every node, I have one multiplexer configured in specific shape. So some inputs get signal from left, go to right, and next one is randomly generated, gets another direction. Oh yes, please press that button. So this array has very many small items. I will show you just in a few seconds what they exactly they're inside. So this is just randomly generated field of cells. Each of them has 6 neighbors. You know, hexagonal lattice. Who played strategy games? They often have hexagonal isometric projection, very convenient to display 3D without actually using 3D. So this is random code, and my idea was we can actually reserve some inputs to work as kind of small cameras. They can be aware about what's going on inside of, what is the state of this node. And we can actually pack the entire information about local node and send it over the wire. And when it arrives to some another special kind of a port, which it does unpack It's like you have a screen and you have people who look on that screen and telling, okay, they look like that. Let's rearrange our local cells so it will look exactly like that cell too. And the rearrangement, they just connect input and output wires. So if you encode this way in random order, it can generate things like this. And if you run it, if you let it go, let it execute this main function, it will start generating very strange, weird patterns. So the devices, which I was calling FPGAs, they actually operate on very interesting principles. They use multi-cascade multiplexers and hardwired inputs to define these multiplexers, which they call lookup tables. And what they do, they actually run complex combined logical functions. So you know, OR, AND, not, and XOR, right? Everybody does? These basic functions from all kinds of programming and comparison. So, every element here is a multiplexer and it has very complex logical input, which is randomly defined, obviously. And multiplexers, they most naturally end up, if you just run different random combinations, in the most cases they end up with XOR function, and XOR function is great in generating random, pseudo-random numbers. So that's why it creates interesting fractally-like patterns when you just initialize it as random code. But this is not my objective, it's just random code. We can use it for genetic programming or other crazy things like that, but my idea is just to transpile C++, Java code to these things. And let me run another program and I can show you how these nodes look and how they actually work. So this is a very simple network, but let's just start from the scratch. Every node has this, I call them unpacking or controlling input and one packing output. And they can route signals between 6 input and output ports. So I can redefine the direction where they route, like this. Okay, it doesn't work. So I created this element, I can run this simulation, nothing happening. So if I connect a node on the right, I know that this object packs its internal image and sends it over this red small port. Can you see that? And then it delivers here and unpacks immediately. We, instead of doing unpacking immediately, can create a wire node and in fact route it down here. And we can unpack it there. So this node is just ordinary wiring node. It doesn't do any logical function. I use it as wire to deliver message from here to there. This is how non-local communication happens. So when this state, and it arrives immediately as one cycle of the simulation, arrives here, this image, the way how input wires should be connected to output wires, get delivered to this target node, and target node changes its shape. Let me run. The background will become black. That means that simulation recomputes what's going on inside. Okay. I made a delay intentionally so you can see what happened. So this node took shape. This node took shape of this one original, and it is possible to create logic gates and complex combinations of everything. So what's possible with these things, they can run any generic computation. You can write logic functions, you can write addition of numbers, you can write multiplication, division. One member of our team is working on creating the presentation of general computation right now. But still interesting complex problems of how we pass big massives of states of nodes. Essentially, this model is designed to be three-dimensional. We have three-dimensional world. We want to use all layers. So we want to use these elements and we want to add more in all directions so we can scale easier, and we don't use like giant fields to just have flat layers, or think about how we connect them together again so we don't have to introduce interface problem, we don't have to return back. So all this crazy thing is ultimately was not designed. I think because I came up with the idea first, then I started asking what it can be used for. Okay, it doesn't work. What it can be used for. And apparently people were trying to create small modules which can self-reassemble, so they can use it in robotics and in what they call it smart clay. So you can, it's like 3D printing, but in real time and in every point of the space. It's like 3D fax, but without slow waiting while your 3D printer will print the original. It just changes its shape like clay, like smart clay. And Intel promoted the concept, it's called Claytronics, and they popularized the videos, did a lot of research, and then they faced that the humanity doesn't have parallel model of computation still. And here's what I'm trying to do, here's what I'm trying to promote and explain to everybody, that it can work. Moreover, we're working hard to making it working and being super practical. First applications will be just running your typical code, not on conventional processors, but on this inherently parallel CPUs. It would require follow-up, meetup, and explanation why it gets parallel, so you can discover where data dependencies can be resolved and lead to changes in parallel lines. There is no need to run sequential code. And that's where this increase in speed will come inherently naturally. So we can upload all our databases from AWS cloud to this new massive non-local lattice silicon structures, which is basically multiplexers. They're not hard to implement. We have all modern tools to create these devices. But the understanding how to write code in them, how to transfer ordinary programs, we have the roadmap, and we're working exactly on that process, which transfer from ordinary code to these parallel things. So we need to create special support algorithms. As I was using the word, can you guys help me to put it up? Okay, it's okay. So as I said, membrane computing is a very important concept because membrane computing creates encapsulation principle naturally. You can assign some areas on the surface of your cell, on the membrane itself, to be as inputs, another parts of that surface to be work as outputs, and then you can use bridges to connect your subcells together and build complex structures. So here, the complex input signal of switches, communication, not communication, but how inputs of your contained cells should be connected to outputs can be defined by the same multiplexers as input signal. And so they produce very powerful computation with reconfiguration of contents. It does require additional study. It's not something for half an hour. I have a meetup here in Edmonds, so you guys can join at any time if you're interested. I'm not promoting that too much. My goal is to educate you, to help you to learn more. As I said, I would love to follow up on more specific things like C++ programming, like better object-oriented design and introduction functional reactive programming. not functional programming. I'm not expert in Haskell, so how can I teach Haskell if I don't know it yet? I probably never will know in perfect detail. But thank you so much for listening so carefully. Hopefully this thing made a little bit of sense to orient our history for past 100 years, how we invented computing. Hopefully after this presentation you have this question mark. Oh, really? What computing is? Let me start thinking about that. So hope this is excited you about that question and you keep asking that question your entire career, because the answer will change not just your own life, you can contribute to very massive impact of our humanity. Thank you so much for listening.